Okay.
So real quick, Clay sent me a message that said
Yeah.
that he is trying to get on, but
I
he's
see
having
that.
issues.
I saw your text. Yeah, your chat. Thank you. Appreciate that. That's right. Thank you for that. It reminded me I should record this. Yeah, so much less density atmosphere, a lot harder to generate lift. In general, when you're dealing with low Reynolds number, flight becomes inefficient. So that's why a 747 is able to fly a lot longer distance than a Cessna. Bigger wings, faster, bigger Reynolds number. It's generally more efficient. You can travel a lot further distance. So with an atmosphere that's 1% the density of Earth's atmosphere, you lose a lot of efficiency. But I think the other reason they're probably not flying very far is that you're so far away and they don't want to take the risk of losing the vehicle or losing contact with the rover, because it's getting a lot of controls from the rover, and all of the data that the helicopter collects is not going to be transmitted directly back to Earth. It's going to be transmitted to the rover, and the rover is going to transmit that back to Earth. A bunch of really cool mechatronics type stuff in this helicopter. First of all, it's fully autonomous vehicle, so it has to do all of its own navigation. It's using vision-based navigation, so it's got a navigation camera. Whoops, not what I want to do. Trying to highlight that. Okay, it's got a navigation camera, and it's using computer vision to recognize objects. And so I actually do research on this with some colleagues at Air Force Research Lab. But if you imagine if you have a camera taking a series of pictures, so a video camera, and this one's taking pictures every 10 frames per second. As you're moving, the image that you capture is going to change. And if you look at how much that image has changed, so if you can recognize objects from one frame to the next and figure out how far those have moved in the frame, you can back out how far the vehicle has moved, whether if it's rotated or if it's been moving forward. And so they use that to help provide estimates of its velocity as it's flying. And it also has IMUs. Anyone know what IMU is? So an IMU is a type of a sensor. It stands for inertial measurement unit. So it's using inertia to figure out how fast it's moving. What does that sound like to you? Maybe a name of a sensor
like a gyroscope.
Okay, yeah, like a gyroscope or an accelerometer. You heard of an accelerometer before? Okay, so it's just a fancy way of saying an accelerometer. And usually an IMU will measure accelerations in 3 axes or 6 axes. So 3 translation and 3 rotation. Okay. Why does it have 2 redundant flight control boards?
For redundancy, like.
It's probably not something you want to fail, and you can't get to it if you're on Mars.
Yeah, exactly. Nobody's going to be fixing this thing. It's going to fly until it breaks, and then it's dead. And so these, modern electronics are relatively cheap and lightweight, so it's easy to just slap 2 on there. And the way they control that's kind of cool, where they're taking inputs from both simultaneously. And as soon as one fails, the other one can jump in and do the job. I've got an image there on the lower right showing the mechanical setup for the helicopter and how they control. It's really cool. It has cyclic and collective, just like a manned helicopter. And when I was your age, I had no idea how helicopters work. But if you have some free time, look it up. It's really fascinating. It's really cool how they do that. And so they're doing it on this mini helicopter. Now, some more mechatronics type stuff. This has 2 brushless motors that are custom made, and I got the wrong pen color. I'm trying to highlight this. I'll use my mouse. So I'll flip my mouse over that. That's the lower propulsion motor for the lower prop and upper propulsion motor for the upper prop. So they custom made some brushless DC motors. Later in the semester, we'll learn about how brushless DC motors work. Then down here, there's 3 servo motors for each prop. So a total of 6 little servo motors. And this is a picture of that motor here, this Maxon DC motor. Really sophisticated, high quality motor that's very small. And it's actually going to be used with a gearbox to move these different levers to turn the props and create the control for the helicopter. So really cool. One final thing that was really neat, or here's kind of well, that picture came out smaller than I thought it was. This is showing their electronic architecture. But to do testing, the other thing about Mars flight is gravity is different, right? It's smaller. Gravity is about 30% what it is on Earth. So they couldn't properly flight test the actual prototype on Earth unless they somehow reduced its mass, or what they did is created what's called a gravity offload system, where they basically used a fishing line and a constant force motor, which is a way that a constant force motor to basically tug on this helicopter with the fishing line, a constant force to subtract some of the mass of the helicopter so it could fly around as if it were under Mars gravity. That constant force motor is created by using feedback on the tension in the fishing line. So they measure the tension in the fishing line, feed that back to a control system that applies current to the motor and can modulate or change the current to the motor so that it's providing a constant force to pull up on that helicopter to simulate Mars gravity. So pretty sophisticated stuff. All right, so that's going on right now. That helicopter is on its way to Mars, and in February the rover will land, and hopefully we'll get to see aerial footage of Mars. That's pretty awesome to that stuff's going on right now. Jason, what's so funny? You're killing me. Okay. Well, today we want to talk about microcontrollers, and we're gonna take a trip back in time. This is, anyone know what this thing is?
It's like a thermostat?
It's a thermostat. This is an old school thermostat. This is how we used to do things before the advent and proliferation of electronics, especially microelectronics. Things were done mechanically. So back in the day, if you wanted to have a system that would turn the furnace on automatically when it got too cold, you did something like this. There's a couple different versions here. Well, let's look at the one on the right. Here you have this coil of metal is basically like a spring, and it's very reactive to temperature. Okay, so what happens to metal when you heat it up?
Expands.
Okay, it expands. And usually what will happen here is its width will expand and its length will actually shorten. And so as it gets colder, it's going to turn one way or the other. And if it turns enough, there's this paddle here, number 4, that's attached to the end of that coil. And as that coil heats up or cools down, that paddle moves, and at a certain temperature, it will contact that brown, dark colored plunger there, and that will create an electrical contact that will turn on the furnace. And so you have a piece of metal that is acting as a sensor and an actuator. So it's sensitive to the heat. It moves as as the room heats up or cools down, and it will physically create a contact that turns on the furnace. So pretty cool design, right? You know, that worked for a long time. And you can see there's this, you'll still see these in hotel rooms and stuff. You guys probably have them in your dorm room. You know, there's like a wand up here at the top that the user can slide to set what the desired temperature is. And it's probably not very accurate, but it works in the sense that you can adjust it to what your comfort level is. It may not exactly correspond to 72 degrees Fahrenheit, but you can set it, and it will more or less turn on the furnace at the right temperature. This one in the lower left corner is another version of that, and it's kind of cool. It's using what's called a mercury switch. So this little blob down here is a ball of mercury, and mercury is a really good conductor. So when this coil gets to the right angle, basically horizontal, that ball of mercury will float or will fall down, and it'll move over here, and it will connect. It'll create a short circuit between these two contacts, and that will close the circuit and turn on the furnace or whatever it is designed to do. In this case, so a mercury switch might be able to be used to turn on an air conditioner. I actually have some of these, and I have a machine-powered climbing wall in my garage, and it can do different angles. And it's got two mercury switches in there to detect if it's going past the limits, the design limits of how far it's supposed to, you know, how steep it's supposed to go. So if it gets to that certain angle, that mercury switch will close and tell the controller to shut off the motors. That's kind of cool. All right, so we don't do that these days. Now we have things like this, and in fact, I will add, even these are getting dated at this point. Now most homes are going to network-enabled thermostats, where, you know, I have two of them in my house. I can pull up an app on my phone and I can set the temperature. I can program it to schedule to turn the heat on and off at certain times if I know I'm not going to be home. If I'm on vacation, I can check and see how hot it is in my house. But anyway, this is a great example of what we call an embedded system, where we have a Mechatronics system that includes sensors and actuators and a microcontroller, some kind of a brain that can make decisions. In this case, it can interact with the user. It can accept inputs and information from a user. And it has outputs. It can display things to the user, such as, you know, what the temperature is, or it can command different devices to do things, to turn on. And that's what's happening here. I'm going to close the chat. So something that's distinctive about an embedded system, you guys are very familiar with computers, like PC type computers that you're all looking at right now, or mobile phone type computers. And the advantages of those are that they're very adaptable, they're reconfigurable. You can use them to do lots of different things. So think of a phone. It has some basic functionality, but it's basically a device that runs applications. And the applications, the phone comes with some hardware. It comes with a number of sensors, and it's got a speaker and a camera and things like that. But then the applications are completely customizable. You can add applications, and you can basically evolve what your phone does. An embedded system is generally designed to do one thing, or a limited amount of things. It's not generally adaptable or reconfigurable. So you think of this thermostat, engineers design it. They try to anticipate what the user is going to do with it and include the features the user is going to want. Then it's packaged up and it's shipped, and that's what it does. You don't upgrade it. You don't download new apps for it. You don't use your thermostat also as a camera and as a phone and as a navigation device or any of those things. It's designed to do one thing. The advantage of that is it can be a lot less expensive, right? A modern cell phone is in the range of $1,000. Something like this is maybe $20, $25, $30, something like that. The new web-enabled ones are around $100, maybe a couple $100, depending on what they do. This idea of things like devices like this that are web-enabled are part of what is called the IoT, or Internet of Things. You guys heard of that? Internet of Things. And you will see as you go out shopping for microcontrollers, you'll see things that are advertised as IoT enabled. And that means that they probably have a Wi-Fi chip on board so that you can easily connect to the internet with them, and they can share information that way. Okay, so how would we implement an embedded system like this, like a thermostat? Well, we need to have a microprocessor that can execute programs. We need a device to input information as well as to output information or commands, and we need the flexibility to adapt to our changing needs. And so that's what we're going to use, this Arduino Mega microcontroller, and this is what's known as a development board, which is a special type of microcontroller where the controller itself is this black thing here, this black square in the middle. That's the microcontroller. And if you were building that thermostat, you wouldn't put this whole blue board in the thermostat. You would just have that chip and whatever connections are needed to the chip to make it operate. Here, this Arduino is a development board where the chip is on there and accessible so that we can do experiments with it. We can prototype with it. We can try different designs, test them out, and see if they work and refine our designs. This is more of a schematic look at what the microcontroller is, what it's composed of. Ooh, Cody, show that to everyone again. Pull up your, so Cody was just looking at his Arduino. Thank you. I put a poll on our team's website. I've never tried this before, but it looks like an assignment or a quiz. You might have gotten an email. Did you get an email about that you have a quiz has been assigned to you? I'm seeing some nodding. Okay, and that's just a few questions asking you if you've gotten your Arduino yet and if you've tried to install it. If you have not, you need to go see Mr. Rodin in the lab, and I recommend texting him ahead of time to make sure he's there, and he can get that for you. Okay, so this gives some details about what's on the Arduino. There's some key elements here that we're going to make use of. You've got these black things here. Those are pins. These are how we are going to talk to the board, how we're going to interface with it. Well, I misspoke there. We are going to talk to the board by using our USB, sorry about that, our USB cable in our computer, and our USB cable hooks in right here. And so we will program the Arduino through the USB port. But the outside world will interact with the Arduino through these pins. Okay, we have both input and output pins, and most of the pins can be configured to be input or output, and we'll learn how to do that. You'll write some code that sets the pin to be input or output. So these here are digital in, out pins. Okay, so that's shown here in the green. Then there's some other components that are important. We have a voltage regulators and things like that. We'll get into that more in future slides. Okay, but for now, we've talked about that a mechatronic system is something that should be able to sense the environment and then make some kind of decision and or possibly record data and then do something, act in some way to react to what it's sensing in the environment. So if we're looking at sensors, what are different things we might sense? This is the interactive part of the class. So throw some things out there. Unmute yourselves and tell me what are things we might sense.
Temperature.
Distance.
Okay, temperature. Great. I heard distance. Or we could call that range. Tessa, if that was you, I didn't hear you. You say again?
Light.
Light. Very good.
You can sense sound.
Yep.
Speed.
Very good.
Orientation.
Good. Yeah, we could call that attitude. How might you sense that? What type of sensor might you use for that?
Something with some sort of gyroscope in it.
Okay, gyroscope. We also have a magnetic compass. Something some of you may choose to use on your robot at the end of the semester.
Some sort of torque
Changes
or
in-
force.
Good. We have forces and torques. Someone else said
Changes
something.
in pixels or imagery.
Okay. Good. When you get into that, there's all kinds of different versions of image sensors. We humans see light in the visible spectrum. There's infrared. We have different types of radar we can do, or lidar, and basically what you're sensing there is basically 3D terrain. Other things we can sense pressure. We can detect gases or chemicals. Depends on the sensor. So yeah, all kinds of things we could sense. Then there's actors. What type of actions can we take? Or what type of actuators might we have?
Like a servo moving something.
Yeah, so we can have motors for motion. We've got lots of types of there's rotary motors, there's translational or prismatic motors or actuators. Okay, that's probably the most common, what we'd most commonly think of. There's other types of actions we can take.
I remember last year we talked a little bit about like the piezoelectric. So like when you put a charge through it, it moves it.
Sure, and that's a type of motion actuator. Although it can also, a piezoelectric can create sound. So that can be a type of action we can take. We have what are known as piezoelectric speakers, and you'll play with those this semester. This example we're going through right now to introduce class, we're talking about a thermostat. So what type of actions does that take?
Heating or cooling.
Sure, we can turn on a heater. We could have heating elements.
Okay.
Has anyone gotten far enough in pre-lab 2 to do run the program that you're supposed to run. And what does that program do?
It makes the light blink, I think.
Yeah, so could we turn on a light? Is that an action we could take? Yeah, so anyway, lots of different things. You could turn on open and close valves. So it could be doing flow control. What's your car's cruise control doing? It's gonna run in it. It's gonna push on the accelerator. All right. So again, we're using this model of a feedback system where we have something going on in the environment. Then we use sensors to sense the environment and feed that information to the microcontroller. That's compared to some desired state that the user would like. And then some action is taken based on that comparison. And we hope to affect the environment or the state of our system by doing that action. So again, we check to see, did we get the improvement that we want? If not, then we go through the loop again and we take more action. In the case of our final project, you'll be building a robot that's going to go out and search for something on a table. So the state it's looking for is, do I detect what I'm looking for? If so, then I want to drive in the direction of that object. And then I'm going to go, when I've determined that I'm close enough to the object, I'm going to capture it, collect it. Okay. This is an example of a system I designed and built for some of the rock climbing research I do. Down here is the Arduino Mega microcontroller, and I've stacked on some extra components to it. These are called shields, and these are used to add capability to a system. So in this case, there's a display shield, and there's a strain gauge shield that is designed to collect data from strain gauges so I can measure force. And then there's an SD card. So there's an LCD shield, there's an SD card that holds the data that I'm collecting, and there's a strain gauge shield. And this is to measure the force that rock climbers are applying when they're climbing. Here's a prototype, so you can see the Mega down there. This is that LCD shield, and those other shields are stacked behind it. You can't see it there. All right, so let's talk a little bit more about what's in a microcontroller. These are the major critical components. Every microcontroller needs to have a CPU at a minimum, and that stands for what?
Central processing unit.
Very good. Thank you, Adam. I think that was you. Then we have to have some kind of memory. And memory is critical because we need to have a place to store the data that we're going to manipulate. Something like if our sensor is detecting light or not, we need to know that. But also we need to be able to control, or we need to be able to store the instruction. So there's a couple types of memory. Jason, what is ROM? R-O-M.
Sorry, my mic's not working. Read-only memory?
Yes, very good. And so what that means by read-only is we're not going to erase it and write over it. We're not going to change it, okay? And so in the ROM is where we store code or the instructions of what the microcontroller is supposed to do. This is also known as It's known as being non-volatile. Kevin, do you know what non-volatile means?
So I would just say that like non-volatile, it's not gonna like mess anything else up when you go to change something.
Okay, not correct. Does anyone else know what it is?
It retains the
lasts if
memory
the
with the
power's
power.
off.
Okay, Cody, go ahead.
Okay.
Or was that Cody or was that Grant? Right, maybe it was Grant who was talking.
I think it was Grant.
Oh yeah, Grant, what did you say about non-volatile?
It's stable and retains its contents without power.
Yeah, when you turn your microcontroller off, it will still be remembered. Okay, that's going to be really important. You're going to write programs and like for your robot, and when you turn the robot back on, you expect it to turn on and start executing the program. It's not going to remember maybe what the light sensor was reading, because that's memory that's going to be lost when you power off the robot. But it will remember the instructions and it'll start executing the instructions. Okay, so there's a couple types of read-only memory that are common and they're used in your Mega. There's flash ROM and EEPROM. So electrically erasable programmable read-only memory. That's what the EEPROM is. That's what your programs will be stored in. Okay, so RAM is random access memory, and it is volatile. That's where we store the data. So whatever your sensors are picking up would be stored in there. Or if there's some user input that you interact with the user, it would be stored in that type of memory. And when it's powered down, that data is lost. Okay, then we have to have, so the other thing we have to have in order to have a microcontroller is I/O. Some sort of input output, so that we can interface with the world or interact with the world. Other common things to have would be a serial bus. Yeah, I'm going to write this up here. We have to have a serial bus to move things around. This is going to move data and instructions around the microcontroller. We'll typically also have things like a voltage regulator, a timer. Oh. And we might have other more elaborate features depending on how much you paid for your microcontroller. Control registers, A to D converter would be a common thing to have. Oops. So A to D converter. That's analog to digital converter. Okay. So
And
here's a little bit.
question.
Yeah.
When you say we're coding, what language are we coding in, or is it like what is it? Do you mean by that?
We're going to be coding in a modified version of C. It's fairly intuitive, pretty easy to pick up, and we will jump into that in Lab 2. So if you, as you work your way through Pre-Lab 2, you're going to experience coding in C very briefly. You're going to get to look at a program that comes built in on the microcontroller, and you'll make some very simple modifications to it. But it'll get you in there and give you a chance to understand how the code is structured and what it's doing. We'll get into that more later. If we have time at the end of this lesson, we can jump into that a little bit. Okay, so here's some more specifics about the actual microcontroller we're going to be using, the Arduino Mega 2560. This is like the four-wheel drive truck of the Arduino family. It's big. It's got a lot of input and output pins, more than you guys will need, but I'd rather have that than have you limited. But that said, these things are not nearly as powerful as, say, your cell phone is. Okay? They don't have that much memory. They aren't crazy fast. They're designed to be inexpensive and very robust, meaning that they don't break, that they work right all the time and will work for a long time without needing to be replaced. Some important specs: operating voltage is 5 volts. Almost all of the sensors and things that we use will run on 5 volts, so we can get power. So your Arduino has power pins. So if you need 5 volts to run a sensor, you can get it right here on this pin. Will provide 5 volts. The reason I point this out is there are many microcontrollers that run at 3.3 volts. And you may encounter sensors that need 3.3 volts because they're designed to work with those. Well, your Mega has a 3.3 volt pin also. So if you had a sensor that needed 3.3 volts, you could get that there. The strain gauges I used worked better with 3.3 volts, so I used that. Input voltage can be anything up to 12 volts, and you power it through this port right here. If you're going to use external power, you can power it with batteries, you can power it with a wall plug, or if you plug your laptop into it, the Arduino will get power from your USB port, typically about 5 volts. So that will work for doing most of the things we're going to do in the course. But if you're doing things that use more power, like running motors, you may find that it's better to have a separate power source plugged into this black connector. So it's got a lot of pins, 54 digital input-output pins. So that's what I/O means, input or output. And you'll configure them to be input or output with some code that you write. You'll use a command called pin mode to set if it's an output or an input pin. PWM is something you're going to learn about in the reading for next class. So keep your eye out for that term, PWM. It's very important. There might be a quiz on it. Okay, so current, it can provide 20 milliamps, which isn't very much. That is enough to make LEDs turn on. You can get a servo to turn, but it won't turn very fast or provide much torque with that. And you won't be very successful at running like DC motors with so little current. We'll learn later in the course, we'll learn a technique for how to get more current to run motors. A very important thing here, it's a different color and I'm going to circle it, is we can only sync 40 milliamps. What does sync mean? I will take input from anyone. What do I mean by the Mega can only sync 40 milliamps of current?
Does that mean you could
Um,
put out 40 milliamps?
Okay, so we can put out, it can source 20 milliamps, meaning it can put out 20 milliamps. So if your motor needs 40 milliamps, it won't turn your motor. So if that's what source means, what does sync mean?
takes
So
away.
it's
You can only
the current flowing into the op amp.
Yeah, so it can only safely consume 40 milliamps. If you connect a source up to it that's able to provide like a whole amp, you will fry your Mega. you'll fry that pin and maybe other things. Okay, so it's important when you're connecting things that can provide power that you're careful that they don't burn up your mega. And we'll learn techniques for doing that. You're going to use what are known as current limiting resistors to prevent high current from going into your microcontroller. Okay, so we will be doing that. All right, then there's some more details there. Okay, the ROM, 4 kilobytes. That's not a typo. You know, like how much, you guys probably have like a micro SD card inside your cell phone. How big are those SD cards? Mine's 64 gig. I got a 64 gigabyte micro SD card. You might have 128 gigabyte. It goes byte, kilobyte, megabyte, gigabyte. Okay, so what's the point I'm trying to make here? You guys grew up in a world where gigabytes was like the unit of measure of data. You're now going to be working on a device that has only 4 kilobytes of read-only memory, meaning all the programs you write have to be smaller than 4 kilobytes. So we have to be a little bit more efficient than you would be used to doing on your cell phone. You can't have MP3s that are 100 megabytes a piece stored on there, right? Okay. We have a little bit more flash memory that can be used for programs as well, and then the RAM that's for storing data. Okay, moving on. This is just a zoomed in view showing the different components. Okay, so we have to communicate with the microcontroller, and this is how we're going to load our programs. We use the USB. USB is Universal Serial Bus. Whoops. So that's how we'll load our programs onto the microcontroller. You won't have to worry too much about that, but we're going to have to write in a language that it knows. So computers, machines use what's known as machine language. We won't use this, okay? So this is very primitive. It's like it is literally ones and zeros. So this is binary. Assembly language is a little bit more sophisticated in that it uses mnemonic devices for various functions. That makes it a little bit easier for humans to remember what they are and write in that way. But we're going to use what are known as higher level languages and interpreters. We're going to use something called an IDE. There's an Arduino IDE. That's what Prelab 2 is all about, installing the IDE and getting started using it. IDE stands for Integrated Development Environment, and it's where you're going to type up your programs and then compile them and download them onto the Arduino. And what these higher level languages do is they're written in a way to make it more intuitive for you to write code and make it easier to write programs that are going to work well. Okay. So those are going to help us out a lot. And these are the big takeaways, like this is the most sophisticated. The drawback, you might ask, why would anyone ever use like assembly language or machine language? These guys are generally more efficient. You can write programs that use less memory and might be faster than a program written in a higher level language. But it requires the programmer to be extremely knowledgeable and know all of the different functions that the hardware can do. All right, other ways we're going to talk to the microcontroller is through the input-output pins. And those are connected to sensors, which get information about the environment, and it's converted into a way that the microcontroller can understand. What is the language of a microcontroller or a computer? Anyone?
Would it be binary?
Yeah, binary. So computers talk in ones and zeros, or with a microcontroller, it's voltages. And we use ones and zeros to represent voltage. So a high voltage is a 1 and a low voltage is a 0. But that's digital. And the real world is analog. So we'll need to, if you think about temperature, you have a temperature sensor, it's not going to tell you it's hot or it's cold. It's going to tell you some temperature within a range. We need to convert that to something that the computer can read. So it needs to be converted to a digital value of ones and zeros and then read into the microcontroller. Some microcontrollers have built-in A to D converters. We do. The Mega has analog input pins A0 to A15, and it's a 10-bit A to D converter. So 2 to the 10 is 1024. And what that means is if we were to read in a voltage on that pin, it can accept a voltage from 0 to 5 volts, and it will convert that to a number from 0 to 1024. And we'll learn more about this in the labs when we actually work with these pins. Okay, so if you connect 5 volts to that pin, it will read it in as the number 1024. If you connect 2.5 volts to that pin, it will read that in as the number 512. Okay, so hopefully that helps you see how you can use that to understand, to read in information. Okay, last slide, and I need to let you go. This is what's going on inside the central processing unit. There's something called the ALU, which is the arithmetic logic unit that actually does the arithmetic. It executes the commands. It adds, it subtracts, it compares things, decides is this less than or greater than, that sort of thing. Then you have the bus, which moves the ones and zeros around the microcontroller to make things happen. Okay, so it's going to move data from, if you've got input coming from the user, it's going to move that data into the controller so that actions can be taken by the ALU. It's going to pull information from memory, whether that's the instructions or data. Okay, so the CPU has the ALU, it has the bus, it has memory, and then there's different types of architectures. The reading talked about the Harvard architecture, which is basically what's used by the Arduino, and the von Neumann architecture. Okay. If you'd like to learn more about how these work, really cool YouTube video here. Highly recommend it. Okay, what else? This is just a funny meme. And the rest of the slides just show some fun videos of different projects you can do with an Arduino. So encourage you to take some downtime and follow those links and be inspired by cool things you can do. Like here's a fire-breathing animatronic pony that someone built using an Arduino. Okay, that's all we have time for. Thank you for your attention. This lecture has been recorded, so it'll be posted on the Teams channel. Next lesson is another lecture. We'll be remote just like this. Please do the reading. There's going to be a quiz. If you haven't already, go get yourself a Mega from the lab and start trying to get it working on your computer. We'll be doing the lab on Monday, and you don't want to waste time getting your Mega working. So the sooner you can try it and find out if it doesn't work, the earlier I can help you fix that. Okay, Thanks again. Sorry for running over. Have a great week, everyone.
Thanks, sir.
Thanks, sir.
So guys,
Yes, absolutely. Is this something that other people might want to hear?
it was about the skills review and
Okay. Oh yeah, skills review. I didn't hear you. Go again.
I don't think like it would be relevant to other people necessarily.
Oh, okay. Well, is it a technical question?
Oh yes, sir.
Yeah, go ahead.
For the skills review regarding, can I share the book with you?
Sure. I'm going to stop sharing my screen. Go ahead.
Okay, can you see the book?
It's pulling up. I don't see it yet.
Okay. Basically, just because I haven't taken ECE yet, I was pretty confused with the last question of the skills review involving like the capacitors.
Okay.
And I was just like I was trying to work through the math in the book in like chapter 6 regarding that.
Okay.
Not working out for me, so I was just trying. And basically just like looking at the discharge, like circuit, and saying that like the voltage of the resistor and the capacitor would be equal when the circuit's discharging, and that didn't make sense to me because I don't understand how it would like sum to 0 if those are the only two elements in the circuit.
I don't see. Is there a circuit diagram you're trying to show me? And I can go. I have the book right here. I can go to the page. Go what page it is. It's chapter 9.
It's on page. That's what the graph I'm looking at. The circuit's a little higher, I think.
Okay.
On 163.
163.
The circuit.
So you said that it said something like the voltages were equal where?
On 164, there's the graph that says VC and VR are equal.
At a certain point in time.
When it's discharging, I believe. I'm looking at the one at the bottom of the page.
The graph at the bottom. Okay.
Yes, sir.
Okay, so what's happening there is once that switch is in position A, at the beginning, you move the switch to position B and you leave it there for a long time. Okay, and what happens is the voltage source gradually charges the capacitor until it reaches its maximum charge capacity. Okay, and that maximum capacity is going to be whatever the voltage of the source is. So if that source is 5 volts, you move the switch to position B, that capacitor is going to charge up to 5 volts. It doesn't happen instantaneously. It happens exponentially, which is what's shown in the curve there in figure 9.24. See the gray line in figure 924? It takes a minute or takes less than a second, but it takes some time for that capacitor to charge up to 4.96 volts. So think of
Yes, sir.
think of a capacitor as like a tank of water, okay? And you can fill it up, but it takes some time to fill it up. But eventually it fills up to a maximum amount. Then you flip a switch, and that's like opening a drain on the capacitor. And the drain has a certain size. Adam, are you still with me?
Yeah, so I'm having like a lot of connection issues though.
That's fine. Yeah, and you can turn off your video. I don't need to see you. If you want to share a screen, you can. Okay, so imagine you open a drain on that tank of water, and now the water's going to leak out. That's what's happening when it's going through the resistor to ground. The resistor is like the size.
Because I'm having trouble hearing you.
Testing. I'm turning off my video. Testing.
Sir, I think it's his connection. I can hear you just fine.
Okay.
I can hear you now.
You can hear me now. Okay. So yes, speak up if I drop off or hit the raise your hand button or something. Okay, so imagine you've got this tank of water and it's got a drain on the bottom. What's that? Okay. You have a drain on the bottom of the tank. The size of the drain hole is like the resistor. So a big resistance would be a small hole. So the water can't drain out very fast. Okay, we've lost Adam.
All right, sir. Since I got this kind of in between state, I just wanted to apologize for being late. I was not able to get on MissionNet in the Mech lab.
Okay.
I tried all my computers and my phone, and then I ran upstairs to go to Exemplar Hall to get on the Boingo Wi-Fi. But that's why I was late.
Okay, no problem. I understand.
And
This is
Oh, sorry. And then my other question was, do you want us to email you the skills review or?
yeah.
Okay.
Yeah, and I'm having trouble. I can't get on. I haven't been able to get on like usafa.edu. And so I was going to email you all before class telling you, hey, scan your skills review and turn it in by COB. So when I get that working, I'll be sending an email.
Okay. COB today, correct?
Yeah.
Okay. Thank you, sir. I will send that to you here shortly.
Okay, you're welcome.
All right. Bye-bye.
Sir, could I ask another quick question about the skills review?
Sure.
I'll share my screen with you real quick if that's all right.
Okay.
Just let me know when that pulls up for you.
I see that.
Okay. So I was looking at number 6, and I wasn't sure exactly what we were trying to do, but I see that these different lines you have. I assume that at each of those points you want the 12, the 9, and the 5 volts. Is that correct?
Yeah. Yeah. So imagine
Okay.
if you had a 12-volt battery, but you had different devices, and some of the devices needed 12 volts, some needed 9 volts, and some needed 5 volts.
Okay.
This is a real life situation.
Okay.
This happens all the time. You can create those different voltages by using resistors in series.
Mhm.
Like,
So I got kind of confused then because for R1 here, you have 12 volts leaving the battery, and I found the current, the max current that we can use with the power limitation. But then if we need 12 volts still at that first level there, I was assuming then the resistant R1 would have to be 0 but I didn't know
No,
like that.
yeah, no. Sorry, that I should probably have another line above R1.
Okay, okay, that makes a
That's
lot
where
more
12
sense.
volts comes from.
Okay,
Or 12 volts you would just take right off the power source.
yeah.
The
Okay,
line
so
between 1 and 2 is for the 9 volts.
gotcha. Okay, that makes a little more sense.
Okay.
Okay, I'll go back and rework that one.
Okay, and there's an easy way to do this and a hard way to do this.
Okay.
So if you already know the current, you figured out the current, and that
Mhm.
looks right to me. And you know this bottom one, you can't see. I'm sorry, I'm moving my mouse and you can't see my screen. The
Okay.
bottom one has to be 5 volts,
Mm-hmm.
and you know the current. Well, so you know Ohm's law, right?
Yes.
Okay, so you should be able to figure out what R3 is immediately.
Gotcha.
Then you should be able to do the exact same trick to get R2.
Mm-hmm.
And then once you have R2, you should be able to get R1.
Okay. Sounds good. Yeah. Okay, that cleared it up a lot. I was kind of confused on that earlier, but I should be able to work it out easily now.
Okay.
Yeah. Okay. Thank you so much, sir.
Yep, no problem. Adam, are you back?
Yes, sir. I think I rejoined the meeting, so I'm hoping that it works.
Right. Okay, so what's going on there in figure 9.25 is if you look at so what we're saying there is you've got this capacitor, it's like a tank of water. In the first step, you're charging the capacitor, you're filling up the tank. And there, the voltage in the capacitor is rising. The voltage across we describe as a voltage on a resistor, we say it's the voltage across the resistor because the voltages will be different at either end of the resistor if there is current flowing through it. If there's no current flowing through a resistor, then it has no voltage drop. And that comes from Ohm's law. Do you know what Ohm's law is? V equals IR.
Yes, sir. I
And you talked
understand.
about that in physics,
Yes.
right?
I understand, yeah, from like physics, that concept. My
Yep.
only question is just like with the specific signs when it's discharging, wouldn't they
Yeah.
have to be opposite? Like the sign of
So
the voltage
that
during the
Yeah, so
capacitor.
that Kirchhoff's voltage law would work.
Yes, sir.
Yeah. Yeah, technically that would be correct. That you would say that if the capacitor had positive voltage, then, but I guess the way that makes sense to me to describe it is once you've moved that switch to position A, that voltage source is no longer part of the circuit. We can totally ignore that. All we have now are two things hooked together. We have a capacitor and a resistor and then ground. And whatever voltage is in that capacitor is being dropped across the resistor because on the other side of the resistor is 0. So if you looked at like a point in time and the capacitor voltage was 4 volts, and then you go to that 4 volts goes into one end of the resistor, and then on the other end of the resistor, the voltage has to be what?
-4 or
No, it's 0. By the time you get to the end of the resistor, the voltage is 0 because that resistor is connected to ground. Okay, so ground is always 0. It's an infinite sink. So it will always be 0 no matter how much voltage you try to put on it. So well, let me see. Can you see? I'm going to try to draw a picture that I find it helpful. Can you see my screen?
Yes, sir.
Okay, so okay. this is ground. And then what we do when we're going around this circuit, there's a capacitor, and then there's a resistor. Okay, and this is all ground. So if we start here and we go counterclockwise, we start at ground, we climb up to the capacitor, and so this is like voltage here. We get up to 5 volts, and then we go to the resistor, and we have to go through the resistor, and we have to drop 5 volts and get back down to ground. Okay, so there's a 5 volt rise here going over the capacitor, and then there's a 5 volt drop going across the resistor. So plus 5 volts, minus 5 volts. So that if you did Kirchhoff's voltage law, they would add up to 0 as you go around the circuit. So I understand where your confusion is, in that you're thinking they should be equal and opposite. And I agree with you. I think think of this curve, this figure 925, think of it as being the absolute value of the voltage.
Okay, that makes sense. I think I was just confused because then when you go to solve for the equations, like the equations don't satisfy VC equals VR. But I think I understand now. I just have to start with the equation 0 equals VC plus VR, and then it should work out.
Right. And so it's, well, the point they're trying to make is there's only 2 circuit components there. So the voltage on one has to balance the voltage on the other.
Got it.
And that's different from what's going on in the previous figure. Adam, if you need more help on that problem, because you haven't taken double E yet, let me know. And if you want, if we need to schedule EI, we can do that. And if you need to turn it in late, that's fine too.
Okay, thank you, sir. I think I got the energy of the capacitor and the energy discharged by the resistor to be equal. So I think I understand the.
Okay, what'd you get for energy?
5 millijoules, I think.
Yep, perfect. Good.
Okay, thank you. That makes a little more sense. I think the book was just throwing me off with a few things, but I should be good.
Cool. Is that it?
Yes, sir.
Okay, cool. I gotta stay on and talk to Cody for a minute. I'm gonna stop recording.